Fusion. In fusion, small isotopes combine to make a larger isotope. So the energy is released when the two light nuclei combine. Here we have deuterium, which you might remember is hydrogen 2, and tritium, which is hydrogen 3. When they combine, they create an alpha particle, 2 protons and 2 neutrons, and a neutron is released. Lots of energy is released, so that's what this symbol represents, 3.5 mega electron volts. In fusion, a large amount of energy is needed to start the reaction, because that energy needs to help those nuclei overcome the repulsive forces of 2 positive nuclei. High temperatures can provide this energy. When they combine, we see mass changing to energy. So you might recognize this as Einstein's equation. Maybe you've seen it, just E equals mc squared. The delta just means you have a change in energy, and here you have a change in mass. The c is the speed of light in a vacuum. So a small amount of mass can release a huge amount of energy, because the speed of light is a value of 3 times 10 to the 8th meters per second, and you're squaring it. So you might remember as you square it, it becomes 3, let's square the 3 as well. So 9 times 10, remember if you're squaring, you multiply it by 2, times 10 to the 16th meters squared, second squared, and you'd be multiplying that by a mass. And that gives you your energy. We call this, when the reactions have a small mass change, a mass deficit. The sun is our most familiar fusion reaction, and so in the sun we have lots of hydrogen changing to helium, and the hydrogen is deuterium, hydrogen 2, and tritium, hydrogen 3, changing to helium 4. We're trying to replicate this on Earth, but just looking at this flow chart, and let's start over on the left side, we have 2 hydrogen 1 nuclei. They hit each other and they become hydrogen 2. That's your deuterium right here. That combines with another hydrogen and it can make helium 3. The helium 3 combines with itself, and here's a helium 4. So this is a different pathway to helium 4. On Earth, we can use magnetic fields to contain the superhot material. At Lawrence Livermore Labs, they're using a facility called the National Ignition Facility. This is the main reaction chamber that they were lowering into the ground. It's probably about 6 stories below ground level. And that's what it looks like. So the part that you're looking at is, this part is right here. So I was able to visit this a few years ago when I was attending a workshop, learning about new activities for you guys. They use these crystals within these chambers, so it has a bunch of lasers that all focus on isotopes of hydrogen to try to create fusion. And this crystal, which is just a phosphate crystal, focuses the lasers. The target is ever so small. So there's the scale of a woman holding the target, and you can see how tiny it is. And the numerous lasers focus on that target to create fusion. And unfortunately, they haven't been successful yet, but we'll see what happens.